Swayam Prabha. Digital India. Educated India.
Welcome back to lecture number 23 on the topic refrigerant and its properties in the subject thermodynamics and thermal engineering. Let's have a quick recap on what we have discussed in the previous lecture number 22. So, we have discussed about the construction and working principle of a vapor absorption refrigeration system. So, we have discussed about two types of systems. One is water lithium bromide system, in which water is the refrigerant, lithium bromide is the absorbent, and ammonia water system, wherein ammonia is the refrigerant and water is the absorbent. We have seen the thermophysical properties which are required for the refrigerant, absorbent and the mixture. Mixture refers to the solution which is a combination of refrigerant and absorbent. In case of water lithium bromide system, there is no need for a rectifier, because the refrigerant vapor, which is the water vapor coming from the generator, it is pure refrigerant vapor. It does not contain any carryover of lithium bromide. So, the refrigerant vapor, that is the water vapor, is directly condensed from the generator without the incorporation of a rectifier. Whereas, in case of ammonia water system, the refrigerant vapor, which is ammonia vapor coming from the generator, it carries some amount of absorbent, that is the water carryover, so which is removed in the rectifier. So, during the process the heat is ejected to the ambient, and the absorbent which has been removed, it has been sent back to the generator, and the purified refrigerant vapor is condensed in the condenser, then throttled before it is evaporated, and the cycle continues. If you see compare the performance of the water lithium bromide and ammonia water system, water lithium bromide system has a COP, a coefficient of performance of the range 0.6 to 0.65 or 0.7, which is slightly higher COP than ammonia water system, because the reason why the ammonia water system has less COP than water lithium bromide is, that is due to the rectification, due to the absorbent carryover. Even after purifying the refrigerant vapor in the rectification, in the rectifier, still there will be traces of water carryover, like about 0.5% or even up to 1% it is there. So, 100% pure vapor coming from the rectifier, it is a challenging one. The COP of the system is the ratio of refrigerating effect, that is the cooling capacity, to the heat supplied in the generator. In the generator, external heat from the external source is provided. The external source could be solar energy, waste heat, steam, process heat from the industries that could be used. So, because of this one, this absorption system is known as, it is a heat operated system, and the power requirement, the electrical energy requirement for this system is very small. The power is required only to operate the solution pump, which pumps the strong solution from the absorber to the generator through a solution heat exchanger. Again, when it comes to solution, we have strong solution and weak solution. Strong solution means a solution which is strong in refrigerant and weak in absorbent, and weak solution is just opposite to the strong solution, which is weak in refrigerant and strong in absorbent. So, the energy balance in case of an ammonia water system is the heat added in the evaporator, QE plus QG, that is heat supplied in the generator. It will be equal to the heat rejected by the absorber QA plus heat rejected by the condenser QC and heat rejected by the rectifier QR. In case of water lithium bromide system, the energy balance is QA plus QC is equal to QE plus QG. And these systems are available in capacities from 3 tons to 5,000 tons of refrigeration. And in terms of applications, water lithium bromide system is used for air conditioning applications. It is not used for sub-zero or negative temperature applications due to the freezing point of water at 0 degree centigrade. So, it is not recommended to use below 3 degree or even 5 degree centigrade. Whereas, ammonia water system is used for refrigeration applications or cold storage or food processing, dairy applications, etc. The freezing point of ammonia is around minus 78. So, we can very well use up to minus 70 or minus 72 degrees centigrade. Now, let us see the contents in this lecture number 23. Refrigerant, what is a refrigerant? What are the types of refrigerant? What are all the criteria that is required while we are selecting the refrigerant? What are all the desirable properties? What are all the properties? Thermophysical properties, chemical properties, properties pertaining to the environment. All these things will be discussed in this lecture. So, the contents of lecture number 23 are refrigerant, history of refrigerant, primary and secondary refrigerant, that is, then how the refrigerants are further classified, selection of refrigerant, comparison of refrigerant properties, designation of refrigerant, which is very important because there are numerous refrigerants have been developed all these years. So, it is not a small number. So, how the refrigerants are designated, how they are referred, and sample calculation of TEWI, total equivalent warming impact. So, first of all, what is a refrigerant? Refrigerant, it is the working fluid which is employed in a refrigeration or an air conditioning system. It can be a single substance or a mixture of substances. If we take the vapor compression system and the vapor absorption system, in case of vapor compression system, the refrigerants which belong to CFC, chlorofluorocarbon, or hydrochlorofluorocarbon, HCFC or HFC, most of these refrigerants are single substance. It is not a mixture, it is not a combination of two or more refrigerants. Of course, refrigerants which are belonging to azeotropic mixture or zeotropic mixture, those refrigerants are not a single substance, they contain two or more refrigerants. So, that is those refrigerants are in mixture form. In case of absorption system, we have seen two systems, both are environment friendly. Water lithium bromide system, water is the refrigerant, lithium bromide is the absorbent. The combination is called a solution. It is called working fluid pair. I mean, it is two working fluids, like one is refrigerant, another one is absorbent. And in case of ammonia water system, ammonia is the refrigerant and water is the absorbent. And this refrigerant, it is a substance which absorbs the heat in the evaporator, undergoes phase change, where the liquid refrigerant is converted into vapor refrigerant, low pressure refrigerant vapor, and again the refrigerant undergoes phase change in the condenser, where the vapor form of refrigerant is condensed into liquid form. These refrigerants are selected based on the thermodynamic properties. Again, this point will be repeated in one of the slides, a subsequent slide, because since it is very important. So, I have given in the introduction of the refrigerant as well also under the heading selection of refrigerant. Normally, when we design the system, suppose the design of a system, the cost, the operating cost, the initial cost, the reliability of the system, how easier it is to do service in case if there is any maintenance of the system is required. All these things depends upon the nature and the type of refrigerant which is employed in the particular system, which is particular. Let me repeat it again. The design of the system, the size of the system, the reliability, cost, initial cost, operating cost, the maintenance cost, and the extent to which it can be easily serviced when there is any maintenance work is required. All these things depends upon the type of refrigerant which is normally employed in the system. So, as I mentioned, the system design cost depends upon the selection of refrigerant. This table highlights a brief history of refrigeration. Of course, it is not, if we go into the detail, it will take more time. So, due to time constraint, I have just summarized the inferences from the history of refrigeration in the form of a table. In the year 1755, William Cullen, he designed the first refrigeration machine. Later, about 50 years later, Oliver Evans described the vapor compression system. VCS stands for vapor compression system, to produce ice by using ether. Then in the year 1834, Jacob Perkins developed the first vapor compression system, refrigeration system. 1850, Alexander Twining, he patented the vapor compression system which was employing ethyl ether as the working fluid. Then in 1856, James Harrison patented vapor compression system using ether, alcohol and the ammonia. So, ammonia is the natural refrigerant which is there, which was used at that time. Okay, so this is again in 1860, Ferdinand Carre patented the vapor absorption system. The first absorption system was patented using ammonia water, in which ammonia was used as the refrigerant and water is the absorbent. 1879, first refrigeration system using R744, that is CO2. 1928, General Motors developed a system in which they developed the refrigerant R21. 1931, commercial production of R12 and R11 and R12, that is refrigerants belonging to CFC group, chlorofluorocarbon group, by General Motors and DuPont. So, this is about a brief. So, if you see the history, so the history of refrigeration has started way back in the year 1755 and lot of developments have taken place. Maybe some of the systems were not that much efficient, though the design was successful. When they evaluated the performance of the system, it was not up to the mark. So, the design has been modified. The eminent personalities or scientists who worked in the subsequent years, they have modified the design and have proved some of the systems to be successful in reality also. So, the history goes from 1755 onwards. Difference between primary refrigerant and secondary refrigerant. So, the primary refrigerant is used directly in the system. Okay. So, it is called like a direct expansion system, DX system, where the refrigerant is directly used and also it undergoes phase change in evaporator as well as in the condenser. Examples of primary refrigerants are, you can tell this R11, R12, R22, R134A, R407C, propane, etc., ammonia, sulfur dioxide, carbon dioxide. Okay. When it comes to secondary refrigerant, these refrigerants are not used for cooling directly. Of course, they are used to transport the energy, okay, used to transport the energy from one place to another place. Like the refrigerant will be used to cool the water. So, the chilled water will be circulated, it will be used to cool the air. So, that means here the refrigerant is not directly cooling the air. So, the refrigerant is cooling the medium water, which in turn is used to cool the air. And this secondary refrigerant, they do not undergo phase change either in the evaporator or nor in the condenser. Examples are chilled water, ethylene glycol, that is the brine. So, generally these solutions are referred to as brine or antifreeze agents which are used. Suppose if you are using water as the refrigerant, because of its freezing point at 0 degree, it cannot be used for sub-zero temperature applications, that is negative temperature applications which demand which applications wherein the temperature is below 0 degree centigrade. So, in such cases what they will do is they will use some salt like calcium chloride, it is available in the salt form, or ethylene glycol, like that. So, some antifreeze agents will be used, that will be used with the medium. So, this is the previous classification is based on the type of whether it is providing the cooling directly or indirectly, whether it undergoes phase change or not. This table shows the classification of refrigerant, according to its properties, and also whether it is environment friendly, various properties. It could be based on the thermophysical properties, depending upon its molecular structure, etc. So, under pure fluid, if you see pure fluid, there are two types of substance refrigerants. One is synthetic, another one is natural. These synthetic refrigerants are nothing but artificial refrigerants. Refrigerants are, in other words, man-made refrigerants. Man-made refrigerants. These CFC, chlorofluorocarbon, hydrochlorofluorocarbon, HFO, all these categories of refrigerants fall under synthetic refrigerant, which are all created by man, artificial. Example for CFC is R11, R12, then HCFC we have R22 and R123, then HFC R134A, R404A, okay, and HFO, HFO1234 YF and HFO1234 ZE, okay. So, these refrigerants generally have very, especially these HFO based, they have very low boiling point. Natural, then under the classification of natural refrigerants, it is further classified into two types, organic and inorganic. Organic refrigerants, examples are refrigerants based on hydrocarbons like propane, N-butane, isobutane. N-butane and isobutane are isomers of butane. Okay, so C3H8, C3H8 is propane, C4H8 is butane. Then in inorganic, we have the natural, this one is ammonia, molecular weight of ammonia is 17. So, R7 is the series, is the designation which are used for inorganic type of natural refrigerants. 718, that is 18 is the molecular weight of water. Then air, 729, 29 is the molecular weight of air. So, the first refrigerant, this is ammonia, then water, air, carbon dioxide, and of course, SO2 is also there, sulfur dioxide. Then, so all these things are pure fluids, that means single substance. The refrigerant is used as a single substance, not a mixture. When it comes to mixture, there are two types of this one, azeotropic and zeotropic. So, example for azeotropic mixture is R500 series, like to be more specific, R500, R502. Similarly, for zeotropic, all the 400 series refrigerants are examples of the zeotropic, R404A, 407C, R410A, all these things are zeotropic. So, the difference between the azeotropic and zeotropic is, in case of azeotropic mixture, the composition does not vary between the liquid and the vapor state. So, the refrigerant behaves as if it is like a pure fluid, whereas in case of zeotropic, there is a variation in the composition between the liquid and the vapor state. Once again, since it is very important, I have mentioned these points again, though it is repeated. Selection of refrigerant based on 4 different properties, thermodynamic and thermophysical. So, when I say thermophysical, it is thermodynamic and thermophysical properties. Second one is environmental and safety properties. Third one is chemical properties, and fourth one is economic properties. So, these are all the criteria based on which a particular refrigerant is selected. Let us see the properties in detail one by one. So, thermophysical properties. So, the first and foremost one which a refrigerant should possess is high evaporator pressure. When I say high evaporator pressure, it should be a positive one. That means the pressure should to be more than the atmospheric pressure. So, that means here P, the evaporator pressure should be more than the atmospheric pressure. So, what is the advantage of when we have a positive pressure in the evaporator? So, suppose if the pressure in the evaporator is less than the atmospheric, okay, negative pressure is there. So, there are obviously there will be the air will be entering into the evaporator because due to the pressure difference, and moisture content in the air also will be getting into the system. And once these things get into the system, and removing these things, it is not a easy one. Making an overhaul of the system is a time consuming, and also it is a tedious process. So, rather than maintaining a low pressure than the ambient in the evaporator, so it is always recommended to have a positive pressure more than the ambient for the, and also the advantage of having a high evaporative pressure or a high temperature. When we have a evaporator temperature, so the corresponding saturation pressure we can find out from the property table, or if we know the pressure, suction pressure or the evaporator pressure, the corresponding saturation temperature can be found for that particular refrigerant from the table. When we maintain a positive evaporator pressure or slightly higher evaporative pressure, the compressor displacement also will be small. So, that is about the evaporator pressure. So, it should be high. Next one, condenser pressure. It is just opposite. Of course, condenser is in the condenser only the pressure is maximum. If we have discussed about the vapor refrigeration cycle or even the vapor compression refrigeration cycle or vapor absorption cycle, where the evaporator is at low pressure, the condenser is at high pressure. So, the condenser pressure decides the maximum pressure in the cycle, whether it is a refrigeration compression type refrigeration cycle or absorption based refrigeration cycle. So, the condenser pressure should be as small as possible. Of course, both the evaporator and condenser pressure should be positive. It should not be too high. So, the condenser pressure should be as low as possible. The advantage of having a low condenser pressure is, suppose if we have a high condenser pressure, then when the heat exchanger is designed and fabricated, so to handle a very high pressure, because if it is a very high pressure, so the material of construction, the heat exchanger tubes, all these things and all, we cannot use medium weight materials or lightweight materials. We have to go for heavy materials. Once we go for a heavy materials, the cost also will increase, and also the weight of the system will be more. When we add heavy materials, obviously the weight of the particular component will be more, which adds to the weight of the system. So, when we have a lower condenser pressure, so the materials used for the construction of the heat exchanger and the tubes and all can be a lighter one, so which makes that particular component compact, and also the cost also will come down. So, the desired property, whether it should be low or medium or high. So, I have mentioned just before the particular property. In case of evaporator pressure, it should be high. In case of condenser pressure, it should be low. Okay. The third property is latent heat of vaporization. So, this is expected to be high. When we have a high latent heat of vaporization, the mass flow rate of the refrigerant that will be circulated, that will be less. Okay. Because to have the the maximum cooling effect or the refrigerating effect, the latent heat of vaporization to be high, and that will reduce the mass flow rate of the working fluid, that is the refrigerant which is circulated in the system. Fourth property is thermal conductivity. It should be high both for the liquid and for the vapor state. This is required in order to have high heat transfer coefficient. So, this is K value. K value for refrigerant in the liquid state and vapor state should be high. Viscosity should be low for both the liquid state and the vapor state. This is to have the friction losses due to friction, smaller frictional, pressure drop. The pressure drop to have to minimize the pressure drop, and also when we have a lower viscosity one, suppose if the viscosity, generally if we take liquid which has a high which is a very viscous or high, whose viscosity is high, generally the pumping requirement will be high generally. So, especially this low viscosity is required in order to have a smaller pressure drop. So, this is for applicable for both the liquid state and the vapor state of the refrigerant. Next one is specific heat capacity, that is CP value. So, here I have mentioned high vapor specific heat. So, it should be, why I have mentioned vapor specific heat is, in case of the CP of liquid, it should not be high, it should be less small. For the specific heat of the vapor refrigerant to be high. So, the advantage of having a high vapor specific heat is, as the refrigerant leaves the evaporator as it enters the compressor. So, we have seen in the previous this one, there is a chance of superheating. So, the degree of superheat should not be high. We want to have the degree of superheat to be as small as possible. So, in order to have a small degree of superheat, the specific heat capacity of the refrigerant in the vapor state to be high. Similarly, the advantage of having a smaller value of liquid specific heat is to have a large amount of subcooling. Okay. Next one is the boiling point. If the boiling point is low, okay, we can use it for a wide range of this one. For example, because the boiling point of, suppose if you take water and ammonia, the ammonia boiling point is around -33.3 degrees centigrade at atmospheric condition. Water boiling point is 100 degree. So, when we compare ammonia and this one, ammonia boiling point is much lower than that of water. And there are refrigerants whose boiling point are much lower than this one. So, the boiling point should be low and the freezing point also should be low. So, the advantage of having a low freezing point is, again you take the same example of water and ammonia. Water freezes at 0 degree centigrade, ammonia freezing point is -77.8 degree centigrade. So, there is a delta T of 75 degree centigrade, 75 to 77 degree centigrade. So, once the freezing point is in the positive value like 0 and above, so we cannot use that refrigerant for low temperature applications, like applications which demand say -50 degree centigrade or -40 degree centigrade. So, whereas ammonia can be used up to -70 or even up to -75 degree centigrade. Coming to the environmental and safety properties. The refrigerants, it is expected that it should not be a flammable one. It has to be a non-flammable, non-toxic. Of course, the refrigerant which we have discussed just before, the example which I took, ammonia and water. Water is a non-toxic substance, whereas ammonia is a toxic substance. That is one reason why people have fear to use ammonia. Okay, so the refrigerant should be non-toxic, non-flammable, non-corrosive. When I say non-corrosive is, the refrigerant should be compatible with the materials. Let us take the same example of ammonia. Ammonia is not compatible with copper. Ammonia is not compatible with what? Copper. So, if you see even the solution pump which is used in case of ammonia water system, so we cannot use any type of pump for ammonia water system, because the windings, motor windings are made of copper. So, if the refrigerant gets mixed with those windings, if the pump is not properly made or specially designed, which is the case for ammonia water, pumping the ammonia water solution. So, what happens is the refrigerant, it is like it is not compatible with copper, and it like completely corrodes the material. So, the refrigerant which we are selecting should be a non-corrosive one. Then the fourth important property is ODP, ozone depleting potential. Refrigerants which belong to like CFC, all those things and all, most of the refrigerants or those refrigerants, they affect the ozone layer. Okay, they destroy the ozone layer. That is called ozone depleting potential. ODP. So, whichever refrigerant which contributes to this ODP, which affects the environment, so they have been phased out or like this is as per the agreement made in the Montreal Protocol, phasing out of banning of CFC refrigerants. Then people started moving from CFC to HCFC, and again those category of refrigerants also is not environment friendly. Then people started moving to HFC refrigerants, in which R134A is there. Of course, it is still used there. After the Montreal Protocol, the Kyoto Protocol was there. So, that wherein in that agreement, that Kyoto Protocol agreement, phasing out or banning out of refrigerants which contributes to global warming, So, when these refrigerants are released into the atmosphere, they directly affect the environment, it pollutes the environment. So, here both which are the refrigerants which is having, suppose if a refrigerant is having ODP as well as GWP, it is not suggested or recommended to use. Refrigerants which contributed to ODP have been banned or phased or phasing out is there, and GWP refrigerants which especially in our country complete phase out of refrigerants contributing to GWP is not yet this one, it is in the process. Maybe it will take few more years to completely phase out the refrigerants contributing to GWP, higher value of GWP. The ODP of the refrigerant should be 0. That is, it is not small also, it should be 0. The refrigerant should have 0 ODP and negligible or a smaller value of GWP. In one of the slides, I will be showing about the various ODP and GWP values. Okay. TEWI, total equivalent warming impact, and this GWP and all these things are calculated based on the CO2 emission, So, this total equivalent warming impact, there also the how much CO2 emission is there, both directly as well as indirectly. So, that is the difference between this GWP and TEWI. TEWI takes into account the emission due to direct emission as well as indirect emission. So, that I will be explaining in the subsequent, I think the last but one slide with an example. Chemical properties. So, the refrigerant that has been selected should not react chemical, there should not be any chemical reaction. It should be chemically stable. It should mix well with the lubricating oil. Okay. So, either it should miscible with the oil completely, but there should not be a case where the refrigerant and the lubricating oil mixes partially it is mixing, partially it is not mixing. So, then handling those things are little bit challenging one, and the refrigerant should be detected. If there is any leakage, we should be able to detect it easily. For example, though ammonia has a drawback of toxic nature, that is a toxicity is there. Because of this smell, if there is any leakage of ammonia, it can be easily detected. Whereas some refrigerants which do not have a toxic nature, so there are leak detecting devices are available by which the leakage can be identified from the system. The two economic properties which are quite obvious is the refrigerant should be easily available, there should not be any demand for the availability, supply of refrigerant, and also the cost should be this one, economical, it should be cheap, cost should be low. So, in this table shows a comparison of the refrigerant properties. So, I have just randomly taken refrigerants from different categories. R729, it is a inorganic natural refrigerant, that is air minus 194.3. So, I have taken the refrigerant from the boiling point in the increasing order. So, from minus 194 for air, R718 is the refrigerant water, So, boiling point is 100, freezing point is 0. R744, okay, that is carbon dioxide. Then R717 ammonia, you can see the ammonia boiling point is minus 33.3, freezing point is minus 77.7. Then R12 minus 29.8 and minus 158. Then R11 has a boiling point in positive value of boiling point 23.8 and freezing point. So, here I have compiled the refrigerants based on the boiling point and freezing point, especially in the boiling point in the increasing order from top to bottom. Comparison of the ODP, ozone depleting potential, and GWP. R12 is the base based on which this ODP is this one. So, the maximum value of ODP is 1, whereas the R12 has a ODP of 1. It belongs to CFC, chlorofluorocarbon category. Its GWP is, it's a refrigerant which contributes to GWP significantly. Okay. So, this is R22, you see ODP is less than R12 and GWP also is much less than R12, but still it has got a very high value. That is when we select the refrigerant, the ODP should be 0, it should not be even in terms of decimals. So, GWP can be small. Again, when we say small, 1800 is not a small value, 1000 maybe 100 or GWP of 100 or 50, it could be considered small. 500, 1000, 10,000, 5,000 and all, those values are not small. Then R123. So, if the first refrigerant I have taken from CFC, then the next two refrigerant I have taken from hydrochlorofluorocarbon HCFC category, which were the replacements for initially for the CFC, R22 and R123. So, the ODP of the refrigerants compared to CFC category is less for the HCFC category, and also GWP also has come down drastically. R134A tetrafluoroethane, which belongs to hydrofluorocarbon group HFC, not HCFC. Okay, so there is no chlorine atom in HFC, whereas in HCFC it will contain a chlorine. So, R134A, the ODP is 0, which is employed in most of the window AC, split AC, etc. So, ODP is 0, but it has got a high value of GWP. Then R290, that is propane, hydrocarbon category of refrigerants. ODP is 0 and GWP is also excellent. It is in single digit only. R717, I mean two natural refrigerants I have taken. One is ammonia, 717 is ammonia, 718 is water. So, these both are natural. ODP and GWP is 0. Of course, there are limitations like water freezing point is 0, so it cannot be used for sub-zero applications. Ammonia, it is a toxicity, it is a toxic substance, okay. But both are available easily, available in plenty. Now, the comparison of refrigerant based on the properties, comparative refrigerant properties. So, this is classifications like the toxicity level, flammability level. This is as per ASHRAE 34 standard. Okay, so let me write it here. So, this is as per ASHRAE, American Society of Heating, Refrigeration and Air Conditioning Engineers. That is the full form of ASHRAE, ASHRAE 34 standard. ASHRAE 34 standard. So, if under toxicity there are two categories, one is A and another one is B. If the toxicity level is lower, it comes and it is classified as A type, and if it is higher it is B type. Flammability, there are four levels. One means no flammability, that is a completely non-flammable substance. 2 is lower flammability, of course 2L it is a subset of 2, and 3 is higher flammability. So, let us compare the toxicity level and flammability level for 3 or 4 refrigerants. R290 propane, that is A3. When I say A, the toxicity is low, flammability is high. So, that is one drawback of employing a hydrocarbon refrigerant. Okay. If you see the hydrocarbon refrigerant, okay, R290 propane, it has got excellent ODP and GWP. ODP is 0 and GWP is 3. So, it has got from the environmental perspective, it has got excellent property, but because of its flammability, okay, so there is one drawback because of its flammability. So, its usage is limited, or minimized. Okay. R600A, A3 again, R717 ammonia, B2L, okay. That is B is higher toxicity because it is that is the main drawback of ammonia refrigerant, and 2L, okay, the flammability is neither less nor high, somewhat at a moderate level, and R744, that is carbon dioxide, A1, okay, A1 means lower toxicity and no flammability, but the disadvantage of using carbon dioxide refrigerant is R744 is the molecular weight of CO2. So, the drawback of using this one is its critical temperature is 31.8 degree centigrade, 31.8 degree centigrade. So, there is a cycle called transcritical cycle which is employed. Normally, the condensation process is replaced by a cooling process, gas cooling process. Okay. Designation of refrigerant. So, saturated halogen compounds, refrigerants which falls in this category. What do you mean by this halogen compounds? Like compounds which contains fluorine, chlorine, bromine. So, those compounds are called halogen compounds. So, these compounds are derived from alkenes which has a formula CnH suffix 2n plus 2. Suppose if I substitute n is equal to 1, it becomes CH4, n is equal to 1, C1, H2 into 1, 2 plus 2, 4. So, CH4, which is nothing but methane, Okay. So, n equal to 2, so it becomes C2H6, okay, like that. So, these compounds are derived from alkanes, designated as, these refrigerants are designated as R, that is R represents refrigerant, X, Y, Z. What is this X, Y, Z? Where X plus 1 is the number of carbon atoms, Y minus 1 is the number of hydrogen atoms, Z represents the number of fluorine atoms. And if there is any balance, the balance one represents the chlorine atoms. Let me repeat. So, refrigerant are X, Y, Z, like CH-Cl2F2, it contains carbon, hydrogen, chlorine and fluorine. Okay. So, where X plus 1 is the number of carbon atoms, Y minus 1 is the number of hydrogen atoms and Z is the number of fluorine atoms, and the balance one is represents the chlorine atoms, number of chlorine atoms. Inorganic refrigerants. These natural inorganic refrigerants are designated by the number 7. It is designated by the number 7. Of course, R letter is used. So, R7, all the R7 series are natural refrigerants belonging to inorganic category. Okay. Followed by the molecular weight. Air molecular weight is 29. So, how it is designated? Refrigerant R, 7 is for inorganic series, molecular weight of 29, air is 29. So, R7 29. Ammonia molecular weight is 17, carbon dioxide molecular weight is 44, water molecular weight is 18. Okay. Sulfur dioxide it is 64. So, R764. So, this is how the inorganic refrigerants which comes under natural refrigerants are designated. This already I have discussed. Azeotropic mixture 500 series, I have given example R500. So, as I have mentioned before, azeotropic and zeotropic mixture, they are all not single component. Azeotropic they are all mixture of 2 or more refrigerants. So, example is R500, which is a combination of 73.8% R12 and 26.2% R152A. Okay. And this small letter a represents it means it is the isomer, R502, it is a combination of R22 48.8% and the remaining 51.2% R115. So, here we have at least 2 refrigerants, this mixture is containing 2 refrigerants, the example. Zeotropic mixtures are represented by the series 400. So, R404A, it is a combination of R125 44%, then 52% of R143A and R134A, the remaining 4%. So, it is a combination of 3 different refrigerants. Similarly, R407A 20% and R134A and R125 each 40%. This capital letter A does not represent isomer, only the small letter a represents the isomer. This small letter a represents the isomer, okay. And similarly this represents the isomer. So, now let us see the designation of refrigerant: saturated hydrocarbons, that is propane, butane and isobutane, and this should be like N-butane. This is actually N-butane, or we call it as butane. N-butane and isobutane are the isomer. The isobutane is the isomer of the N-butane. Propane C3H8 R290. Here also this is represented by this one R and followed by the number. And here also for propane alone you can use we can find out the designation by using this the previous one. X plus 1 represents the number of carbon atoms, Y minus 1 hydrogen atoms, then Z represents the fluorine atoms. If you apply that concept, we will get 290. However, for butane, isobutane, that concept cannot be used. So, butane is R600 and isobutane is isomer. So, it is an isomer. Okay. So, this is the isomer of butane. So, it has been given the designation R600A. Unsaturated hydrocarbon. All the unsaturated hydrocarbon refrigerants are designated by the letter R followed by the number 1, So, you will find this R1 means unsaturated hydrocarbon. Then 150270. So, this we can here x is equal to 1, y is equal to 5, z equal to 0. So, you can apply in that equation and we can derive the formula. So, due to time constraint I am not doing that one. Okay. Of course, this is the focus of this lecture is the properties, the broad classification, primary refrigerant, secondary refrigerant, classification of refrigerant. Okay. So, whenever we say R1150, R1 is unsaturated hydrocarbon, this 1 represents the carbon atoms, 5 represents the, that is, this is X, okay, this is X, this is Y and this is Z. So, if you see in that formula, the first designation wherein I discussed X plus 1 represents the carbon atoms, Y minus 1 hydrogen atoms and Z is the fluorine atoms. If there is any remaining, then that represents the chlorine atoms. So, how to calculate the total equivalent warming impact? So, this also should be very low, as low as possible. So, there are primarily 3 important environmental factors which is considered while selecting the refrigerant. ODP should be 0, global warming potential should be as small as possible, not in hundreds or thousands, okay. It should be as small as possible, and a total equivalent warming potential. See, the difference between GWP and this one is, as I said before, it takes into account the direct emission as well as indirect emission. You can see direct emission plus indirect emission. This is the formula for direct emission, global warming potential into M into L. I have given the explanation in the subsequent slide. Okay. Global warming potential of the refrigerant relative to, so the GWP is always the GWP of CO2 is taken as 1 as the reference value, based on which the GWP of the other things are this one. Annual, L annual is the leakage rate of the refrigerant in a year, which is in terms of kilogram. Small n is the system operating life in terms of years. M is the refrigerant charge, how much charge refrigerant charge is, how much quantity of refrigerant is charged into the system in terms of kg. Alpha recovery is the recovery or recycling factor, which varies from 0 to 1. E annual, energy consumption, that is the power consumed by the compressor in terms of units of electricity, kilowatt hour. And beta is the indirect emission factor, the unit is kg of carbon dioxide per kilowatt of hour per unit of electricity. So, this is one example which I have taken, calculation of total equivalent warming impact. The refrigerant selected is R410A. The type of system is multi-inverter 5-star, energy efficient ratio 3.3. The cooling capacity of the system is 12.5 kilowatt. So, 1 ton of refrigeration is approximately 3.5 kilowatt. So, we can, if you divide this value by 3.5, we will get tons of refrigeration, TR. Global warming potential of this refrigerant is 2088. I have taken this lifespan, this 10 years. Emission is, see, all these values are based on this one. Okay. L annual, all these data, it is like a case study, the actual data. It is not a simulated one. So, beta, what is beta, E annual, all the explanations I have given. So, for the example which we are calculating, the direct emission and indirect emission. So, these are all the data which are available. Lifespan 10 years, emission 1.1 kg of carbon dioxide per kilowatt hour. This is the M, leakage rate, okay, 1% per year, recovery or recycling was 70%. So, you can calculate the annual energy consumption. Okay. So, this is 3.59 kilowatt hour, assuming the system is run for 8 hours in a day for 300 days in a year. So, you will get the kilowatt hour per year, this much units of this one. Direct emission, again I am using the same formula, GWP value is given, M is given, L annual is given, N is given. All this, N is the life period. Okay, so here we are taking all these values are given. Please refer the previous slide. Lifespan is 10 years. GWP value is given. Leakage rate is given. All the values are given. So, just we have to substitute in this formula, and GWP M is given 1 minus this one. So, alpha recovery is, that is 70%, that is 1 minus 70%, 1 minus 0.7 is 0.3. So, that is what I have written here directly after substituting. So, 11,129 kg of carbon dioxide is released. This is direct emission. Indirect emission, okay, the formula is E annual into the annual energy consumption into kg of carbon dioxide released for 1 kilowatt of hour. So, this is a standard value 1.1 multiplied by the life number of years 10. So, it comes around 95, close to 95,000 kg of carbon dioxide. This is 11,000, this is close to 95. When we add, we get the total emission as 1,05,905 kg of carbon dioxide. So, this is the amount of carbon dioxide released by this system if we take these parameters by one system in a year. So, let me conclude this one. In this lecture, we have seen about the what is a refrigerant, what is the difference between primary and secondary refrigerant, how the refrigerants are classified, the broad classification like pure fluid, mixture. In pure fluid, we have refrigerants like belonging to halogen, CFC, HCFC, HFC and HFO. Then we have got inorganic refrigerants which comes under the natural category. Then we have hydrocarbon based refrigerants whose ODP and GWP properties are very excellent. The properties are very good, and in fact it is excellent. Then we have seen about azeotropic mixture, zeotropic mixture, the difference between the mixture and the other category of refrigerant is, in case of zeotropic or azeotropic mixture, the refrigerants, at least 2 or more refrigerants are used. It is a minimum 2 refrigerants are used. We have seen examples where there is a combination of 3 different types of refrigerants. Then we have seen compared the ODP and GWP of some of the refrigerants, boiling point and freezing point of some of the refrigerants. Based on 4 properties, the refrigerants are selected: thermophysical and thermodynamic properties, chemical properties, environmental and safety properties, and economic properties. So finally, we have seen a sample calculation of total equivalent warming impact. So these 3 environmental properties are very important: ODP, GWP and TWA. So with this, let me conclude the lecture number 23. Thank you.
Hello, I am Shikha Dikshit. I teach psychology and I work with the Department of Humanities and Social Sciences at IIT Kanpur. Today I will talk about what is causal attribution, or how do people understand causes of behavior. Causal attribution is one of the major topics in social cognition in psychology, and this refers to the fact that people attribute causes to their own behavior as well as to behaviors of others. So understanding the antecedent conditions of behaviors and events is one of the major topics in social cognition. Causal attribution is about finding explanations, and these explanations serve a functional purpose, since they are useful in the purpose of planning of behavior and regulation of responses. As far as attribution of causes is concerned, generally people either do internal attribution or external attribution. Internal attribution, when causes are understood in terms of internal characteristics of people, and external attribution when causes are understood in terms of contextual and situational features. The main perspective that is employed in the understanding of causal attribution is the naive scientist perspective, and this has emerged from the research on attribution itself, and it views attribution process as a detailed and systematic causal search. And this is the dominant view about understanding attribution in social cognition. However, in recent time this is not the only view. There are alternative views also which try to understand how people make quick judgments about causality. So now the question is that why is it that people make causal attributions? The answer to this question can be provided in terms of need for prediction and control. People need to predict their environment, and hence it is important for them to understand antecedent conditions of any behavior or any event. Also, causal analysis is related to various other processes other than attribution. It also becomes the basis of regulation of responses. People also develop causal theories based on their experience, and they employ these theories in different domains. As far as attribution theory is concerned, it consists of mainly 3 theoretical formulations. One is the Heeder's theory of naive psychology, the other one is Jones and Davis's correspondent inference theory, and the third one is Kelly's covariation model and causal schemas. There are other areas of psychology also from where some principles have been picked up and extended to understanding of causality. These areas are emotions, self-perception as well as personality. Psychologists have also tried to understand attribution in specific domain areas. Psychologists have tried to outline the different dimensions that people use to understand causality in domains such as achievement domain, that is understanding causality regarding achievement related behavior such as success and failure, depression, helping behavior as well as close relationships.